Okay, so good morning, everyone. Welcome to today's lecture. So today we'll be talking about the method of using row operators to find the determinants of square matrices in an easier way. So yesterday we talked about what is the determinant of a square matrix, right? And according to the definition, we would use something called a Laplace expansion to find a determinant of any square matrices. And the thing is that according to that definition, actually you will have to pick a row or a column, and then you will multiply each entry on that column or row, you multiply that with its corresponding cofactor, right? And then after you have found all the products, you will take the sum of all of those numbers. So the thing is that the cofactor that corresponding to any entry is actually a determinant itself, right? Cofactor is determinant itself. It is only the determinant of a matrix that is smaller in size, but it is still a determinant. So when you are trying to find a determinant of a square matrix, the more zero entries that you have in your matrices, the easier it would be to calculate the determinant. Because as you can see, if you multiply the zero entry with its cofactor, then automatically the result would be zero, right? And also yesterday we talked about how the row operators will affect the determinant of square matrices before and after the operators. So today we will talk about how we would use those operators to make to transform the matrix into a form that is full of zero, right? Full of zeros. And when we got a lot of zero entries in our matrix, it would be easier for us to calculate the determinant. Okay, so let's talk about an example here. So let's try to find the determinant of this matrix A over here. So here I got a 4x4 square matrix. 1, 2, 3, 2, 4, 5, 4, 2, 4. Okay, so here I got a 4x4 square matrix, and I'm going to try to find the determinant of this square matrix. Okay. So as you can see, there are all the entries in this matrix and then zero. So if immediately you use the definition, you use the Laplace expansion to find a determinant of this matrix, it is possible to do that, but it will be very tough things to do because a lot of determinants are waiting for you to calculate, right? So instead of using the Laplace expansion right away, I'm gonna use row operation to make some of the entries zero. That will be easier for us to calculate, right? So in order to make some of the entries zero, we will use the row operators. So it is similar to the fact that we are transforming this matrix into the row echelon form that we have discussed previously last week, right? So let's do it. So here I am going to make the entries, the leading entries in the second row, third row, and the fourth row zero, right? So in order to make this zero, I'm going to multiply the first row with -5 and add that to the second row. Similarly, multiply the first row with -4, add that to the third row, and finally multiply the first row with -2 and add that to the final row. Okay, so we should have a new matrix. 1, 2, 3, 4. So 1 multiply -5, add to 5, you should have 0. 2 multiply -5 is -10, and you add 1, you should have -9. 3 multiply -5 is -15, and you add 2, you should have -13, and so on. So this is your new second row. Similarly, it should be 0, 0. So for the third row, I'm going to multiply the first one with -4 and add that to the third row. Okay, so you should have -3 here. Also -8, -13. And for the final row, it should be -2, -10, and okay. So I'm gonna call this new matrix here the matrix B. Okay, so before we continue with our row operation, let's compare the determinant of the matrix A and the matrix B. Okay, so in order to receive the matrix B from matrix A, I am applying a free row operation to matrix A, and all of them are of the third type, which means I am multiplying some row and I'm adding that to another row. Okay, so yesterday we talked about the effect of row operation on determinants. And especially if you are only using the third type of row operation, the determinant doesn't change, right? The determinant doesn't change. Okay, so I'm gonna put a side note over here that the determinant of B is actually equal to the determinant. So right, so as you can see here, matrix B have 3 0 entries here, right? 3 0 entries. So obviously, if you want to calculate the determinant, the matrix B is a lot easier to calculate the determinant compared to the matrix A. So you can start the process of using row operation here and try to find the determinant of the matrix B, or you can continue using the row operation to make a lot more entries become 0, which I'm gonna do right now. So next, I am trying to make these 0. I'm gonna make these 0, okay? Oh, yeah, there is actually a lot of ways to make this entry 0, but okay, let's see. So in this matrix C over here, I'm gonna multiply the final row with 3. Because here you can see -9, -3 are both multiple of 3, while -2 is not a multiple of 3. So we are multiplying the final row with 3. So everything stays the same except for the final one. All right. Okay, and because we are multiplying the final row with a scalar free, the determinant of the new matrix C is actually 3 times the determinant of the old matrix C. Right, we talked about this yesterday. Okay, so as you can see, all the leading entries now are multiple of 3. I can actually make this and this become 0. Okay, I'm gonna multiply this with 3, add that to the second row, and I'm gonna multiply this with -2 and add that to the final row. Okay, so in that case, you should have the matrix D. 1, 2, 3, 4. 0, 0. Oh, so this stays the same. Right. Got 24 minus, it should be 11. We got 39 minus 17, it should be 22. Right, and similarly on the final row, I'm gonna multiply the third row with -2, and I'm gonna add that to the second row, to the final row. Okay, so this should be 0. This is 16 minus 30, so -14, 26 minus 9. So right. Okay, so from the matrix C to the matrix D, from the matrix C to the matrix D, I am only using the third type of row operation. I am only using a first type of row operation. So the determinant doesn't change. Okay. So if you want to transform this into the row echelon form, you can try to switch the third row and the second row, but it is not required here because you can stop the process of using row operation anytime and then start using the Laplace expansion. So I think the matrix is pretty good now. I'm going to start using the Laplace expansion according to the definition. Okay, so according to the definition, I'm going to multiply. Oh, I'm going to calculate the determinant of matrix D. So I am picking the first column. So all the entries are 0 except for the first one. So actually, when you are expanding along this column, you are taking this one and you multiply with its cofactor, which is the determinant of this 3x3 matrices. Okay, so actually the determinant of one of D should be 1, and then multiply by -1 to the power of 1 plus 1. So why 1 plus 1? Because this one entry over here is in the first column, first row, right? And then you are multiplying this with the minor, okay? The minor 0, 11, and 2, -3, -8, -20. So that's what we have. Okay, so here we got a 3x3 matrix. I am going to continue using the Laplace expansion to calculate the determinant. And now I'm going to continue using the first column because as you can see, the two entries here are 0, right? So before we do that, let's calculate this part. So this is 1, this is also 1, so this is 1, right? So let's calculate this using Laplace expansion along the first column. So we should have -3 multiplied by -1 to the power of 2 plus 1. So this is lying on the second row and first column. So the exponential should be -1 to the power of 2 plus 1. And then multiply this with the corresponding minor matrix. So it should be 11 by 2, -14, and 17. Okay, so this is -1 multiplied 3 is 3. And we already got a definition of the 2x2 square matrices already, so it should be 11 multiplied by 17 minus -14 multiplied by 22. Okay. So you can use a calculator here. This should be 3 multiplied by 495. Okay. Keep in mind that this is only the determinant of the matrix D. We are required to find the determinant of matrix A. So we should do some things to get back the determinant of matrix A. Okay, so let's connect all of these relationships between these matrices. Okay, so determinant of D is equal to determinant of C. Determinant of C is 3 times determinant of B. Determinant of B is actually equal to determinant of A. So if you compare determinant of D with determinant of A, you should have the relationship determinant of D is 3 times determinant of A. Right? And this is the determinant of D. I'm going to plug this number. So 3 multiplied 495 is actually 3 times determinant of A. And I'm going to cancel the number 3 both sides to get the final result. Determinant of A is actually 495. And that is our result. Okay, so that is what we would call using row operation to find a determinant. Okay. You can use a lot of row operation. You can use more than 3 or 2 types of operation, or you can just only use one and then use the Laplace expansion right away. It's up to you. But at the end of the day, the result should be the same, right? The result should be the same. If you want, you can even transform the matrix into the row echelon form. So the row echelon form of a square matrix is actually an upper triangular matrix. And we already talked about the formula in finding the determinant of triangular matrices yesterday. Simply multiply all the entries on the main diagonal. So if you want to do that, it would be a lot easier, but this is good enough, right? Okay, so that is the way we would find the determinant of a square matrix using row operators. So what we're gonna talk about next is one of the application of the determinant. One of the very important application of the determinant. Okay, so we are using a determinant to establish the inverse. Let's call this the inverse formula. So previously, last week, we talked about how to find the inverse of a matrix using the definition. Okay, so today, after we have learned about the determinant of a square matrix, we can actually find the inverse using another way, using a determinant. So, but first, we need to establish some type of definition. So let's start with a square matrix. Let Aij be an n by n. Okay, so we talked about this yesterday. For any Aij, the Ij entry of the matrix will correspond this to the cofactor Aij, right? For any Ij entry in the matrix, we will correspond this to the cofactor Aij, right? So using all of these cofactor Aij, we would be able to construct a matrix, which people will call the cofactor matrix. Okay, so the cofactor matrix of A, the cofactor matrix of A is defined. Okay, so we will denote that as cofactor of A, and the entries of this matrix is simply the cofactor of Aij. Right? Simply you calculate all the cofactor and you put in the corresponding position of the original matrix. You will have the cofactor matrix. And then next, people would define the adjugate of this matrix. Okay, so the adjugate of A is defined. Okay, so the adjugate of A is denoted as ADJ of A, and this is simply the transpose of the cofactor of A. So the cofactor of A will detect the transpose. Okay, the adjugate of A is actually the transpose matrix of the cofactor of A. Okay, so there will be two new definitions. And using these definitions, people have been able to prove the following theorem. People have been able to prove the following theorem. Okay, so we got a theorem over here. So we got a theorem. Okay, so let A be an n by n matrix, then people are able to show that if you take the product of A and multiply that with the aggregate of A, or conversely, you take the aggregate of A and you multiply that with the matrix A, the result is the same. And the result is proved to be, you take the identity matrix I and you multiply that with the determinant of matrix A. Okay, so keep in mind that I is a matrix and the determinant is a number. So this is a scalar multiple of the identity, right? So from that theorem, we got a corollary saying that hence A is invertible if and only if the determinant of A is 0. Or in this case, in order to find the inverse of A, you simply take the aggregate of A and you multiply that with number 1 over determinant. Okay, so once again, the aggregate is a matrix and 1 over determinant of A is a number. So it is a scalar multiple of a matrix. So that is the main theorem of this section, which we will call the inverse formula. Okay, so we are not going to prove this, but we are going to use that to find the inverse of a specific matrix. Okay, so example 8. Okay, let's try to find the inverse of this matrix. 1, 2, 3. 3, 4. Okay, so in order to use this, in order to use that formula over there, you will need to find 2 things. First of all, you will need to find the determinant of A. Next, you will need to find the aggregate matrix of A. In order to find the aggregate matrix of A, first of all, you will need to find the cofactor matrix of A first. Okay, so that's 3 things that you need to do: finding the determinant, finding the cofactor matrix, take the transpose to obtain the aggregate matrix, and then using that formula over there, you will be able to find inverse. Okay, so let's do all of those things. So first, we are calculating the determinant of matrix. Okay, so you can, because A is only a 3 by 3 matrix, you can use the Laplace expansion right away, or if you don't want to do that, you can use some type of row operation like we previously discussed in the first half of the lecture. But I'm gonna use the Laplace expansion right away because 3 by 3 matrix is pretty easy to calculate a determinant anyway. So yeah, I'm gonna expand along the first row. Okay, so the determinant of A is actually equals to 1 multiplied with -1 to the power of 1 plus 1, multiply the determinant of the matrix 0, 1, 2, 1. Then plus 2 multiply -1 to the power of 1 plus 2. And multiply the determinant of the matrix 3, 1, 1, 1. And last but not least, plus 3 multiply -1 to the power of 1 plus 3, multiply the determinant of the matrix 3, 0, 1, 2. Right? I am expanding along the first one. 1 multiply negative, oh, this is 1. So 1 multiply 1 is 1. This is 0 minus 2. So the answer should be negative 2. This is 2 multiply negative 1. So negative 2 multiply with 3 minus 1, which is 2. Okay, this is 1, so this is 3. 6 minus 1 is 6 minus 0 is 6. So negative 2, negative 4 is negative 6. This is 18. So 18 minus 6 is 12. Okay, so as you can see here, the determinant of A is 12, which is non-zero. So according to this theorem, A is obviously invertible. Okay, A is obviously invertible. Okay, now let's try to construct the cofactor matrix A of this. Cofactor. Okay, so you can calculate the cofactor ij separately, and then at the end you put all these numbers into the matrix, or you can write a matrix and you put the formula here right away. It's up to you. So I'm gonna write the formula. I'm gonna put everything here. So for the cofactor A11, it is negative 1 to the power of 1 plus 1, and the determinant of this matrix 0, 1, 2, 1. Max negative 1 to the power of 1 plus 2. Multiply the determinant of 3, 1, 1, 1. 3, 1, 1. Last but not least, we got 1 to the power of 1 plus 3 multiply 3, 0, 1, 2. So that is the first row. The second row, negative 1 to the power of 2 plus 1. Multiply the determinant of 2, 3, 2, 1. Okay, you can continue doing this. 1, 3, 1, 1. Where were we? Oh, this is 2 plus 3. So it should be 1, 2, 1, 3. One, 3, 3, 1. One, 2, 3, 0. So this should be the formula for the cofactor of matrix A. Okay, let's continue here. Let's continue here. So the cofactor of A should be this is negative 2. Okay, so I have calculate this. I'm just gonna give you the results. Okay, this is the cofactor matrix of A. Let's find out if we have made mistakes. Right. Yeah, it seems correct. Okay, so this is the cofactor of matrix A. So according to this formula over here, the inverse of A is 1 over determinant of A multiplied by the adjugate. The adjugate is actually the transpose of this one. Okay, so A inverse in this case is actually 1 over 12. The determinant of A is 12. and multiply with the transpose of this matrix. Okay, so simply using the row of this matrix and write that as the column of the new matrix. Okay, so -2, -2, 6, 4, -2, 0, 2, 8, -6. Okay, and I will multiply 1/12 inside. So the answer should be -1/6, 1/3, 1/6, -1/6, -1/6, 2/3, 1/2, 0, and -1/2. So this is the inverse of matrix A using the formula. Okay. So up until this point, you now have two methods to find the inverse of any matrix. The first one is to use the augmented matrix AI and transform that into IA inverse. Or you are using this cofactor matrix formula over there to find the inverse of. Okay, so you can try multiplying this inverse with original matrix A, and you should be able to find that the result is the identity. Right, we're not going to do that, but if you want, you can try to check that. Okay, so do you have any question? About that formula over there, I am not going to prove that, but if you want to read the proof of that theorem, you can check that in the textbook. It is already stated in the textbook, okay? Yeah, so do you have any question about today's lecture? Okay, that's good.